Analog Electronics Module for Operational Amplifiers. Fundamentals of Operational Amplifiers. Op-amp is a directly coupled high-gain integrated circuit amplifier with two high input impedance input and low impedance output. Here, this is a symbol of op-amp. Here is the inverting input and non-inverting input and output and two supply voltages. Example of op-amp is 741 IC. It can amplify signal having frequency ranging from 0 Hz to 1 MHz. Op-amp has a differential amplifier input stage and a emitter follower output stage. Differential amplifier input provide inverting and non-inverting input. Emitter follower output must be capable of supplying the external load current and must have low output resistance, provide a large output voltage swing. Modes of operation. Single-ended operation. Only one input signal is applied, other one is grounded. Here we can see only one supply is given and other one is grounded. Amplified inverted signal is obtained at output by a equal amplified and in phase signal. The output will be inverted and amplified. Differential operation. Two opposite polarity input signal are applied. That means non-inverted and inverted signal are given together and the output will be non-inverted. Common mode operation. Input are given to both terminals with the same polarity, then the output will be 0. That is, the signal will be, the input is same polarity, maybe inverted or non-inverted. Inverting and non-inverting input. When input acts alone on a non-inverting terminal, the output is same as input. When input acts alone on inverting terminal, the output is inverted. Ideal characteristics of a op-amp. The voltage gain is infinity, the impedance is infinity, the output is 0, bandwidth is infinity, there is no change in characteristics of a features with the change in temperature. When equal voltage are applied at two input terminals, the output is 0. Inverting amplifier. This is the simple circuit of an inverting amplifier. Assume that it is an ideal op-amp, then the differential voltage is equal to 0. Node A is at ground potential and current through R1 is V1 by R1. Also, since op-amp does not allow current through pass through it, the current from R1 flows through RF. And the closed loop gain is equal to V0 by V1, that is equal to minus RF by R1. Non-inverting amplifier. This is the circuit of a non-inverting amplifier. Here R1 and RF form a potential divider and the differential voltage at the input is 0. Closed loop gain equal to 1 plus RF by R1. The gain can be adjusted to unity on proper resistor. We can change the value of the resistor to get the gain as unity. Compared to inverting amplifier, the input of non-inverting amplifier is exactly large as op-amp. Absorb negligible current from the source. Summing amplifier. Op-amp may be used to design a circuit whose output is sum of several input signals such as current circuit is called summing amplifier. There are two types of summing amplifiers: inverting summing amplifiers and non-inverting summing amplifier. Inverting summing amplifier. A typical summing amplifier with the three input signals V1, V2, V3 and with the three resistors R1, R2, R3 and the output is with the resistor RF. Analysis is conducted out assuming that op-amp is ideal one, that is open loop gain is infinity, input impedance is 0, there is no voltage drop across the resistor, hence the non-inverting terminal is at ground potential. Here the non-inverting terminal is at ground potential. Output of a summing amplifier, that is by nodal equation by KCL at node 1 A. Node A we give a KCL equation V1 minus VA by R1 plus V2 minus VA by R2 plus V3 minus VA by R3 plus V0 minus VA by RF equal to 0. When differential voltage is 0 at A, V1 by R1 plus V2 by R2 plus V3 by R3 plus V0 by RF equal to 0. We take V0 by RF to right side and we get the output voltage has minus RF by RF R1 V1 by R1 plus RF V2 by R2 plus RF V3 by R3. The output will be inverted. Non-inverting summing amplifier. Non-inverting terminal is given to a summer. The nodal equation has at the node A is given by V1 minus VA by R1 plus V2 minus VA by R2 plus V3 minus VA by R3 equal to 0. Then V out equal to, by simplifying we get V out is equal to 1 plus RF by R whole into VA. Open loop configuration of an op-amp. Open loop indicate that no feedback form is fed to the input from the output when connected in open loop. The op-amp functions as a very high gain amplifier. The three types of open loop configuration amplifiers are differential amplifier, inverting amplifier, non-inverting amplifier. In all open loop configuration, only very small input voltage can be applied. Even for voltage levels slightly greater than 0, the output is driven to saturation, that is to peak level. Differential amplifier. Here input is applied both inverting and non-inverting terminal. Here the input V1 and V2 are applied at both terminals. The difference between the input and output is taken. Here V1 and V2 input voltage and R1 and R2 are negligible resistors. Thus the voltage drop across the resistor assumed as 0. Then the voltage output equal to A into V1 minus V2. Inverting amplifier. Input is applied to inverting terminal. Non-inverting terminal is grounded. Here the non-inverting terminal is grounded and input is given to the inverting terminal. Then the output voltage is equal to minus A into Vi. In non-inverting amplifier, input applied to non-inverting terminal, inverting terminal is grounded. Here input is given to the non-inverting non-inverting terminal, and non-inverting terminal is grounded, and the output is equal to A into Vi. Concept of virtual ground. Assume an ideal op-amp. The input impedance of an op-amp is ideally infinity. That we have studied before, that in an ideal op-amp the input impedance is infinity. Hence current I flowing from one input terminal, then the other will be 0. Thus voltage drop across R1 is 0. Both input terminal will be at same potential, that is virtually shorted. Output voltage equal to gain into differential voltage. Then the differential voltage equal to output voltage by gain. For ideal op-amp, voltage is gain is infinity. Then differential voltage is 0. Thus potential difference between two input terminal is 0. When we short circuit, two points will have same potential, that is 0. Due to this reason the two op-amp terminals which are almost equal potential are to be virtually grounded. Negative feedback of an op-amp. Feedback refers to taking an output signal or a portion of output signal and returning to the system input. Here we can see a simple block diagram of an negative feedback op-amp. Here is a controller, source, op-amp gain, open loop gain, load and feedback. Here when source gives an voltage, then it is returned by the feedback to the source again. We create negative feedback by taking the output signal or a portion of that and combining with the input signal via subscription. Overall gain of negative feedback system is called closed loop gain, that is equal to A by 1 plus beta, 1 plus A beta. At A is very large, that is gain is very large, then closed loop gain equal to 1 by beta. In a op-amp, we create negative feedback by connecting feedback signal to inverting input terminal. Here we can see feedback is given to inverting terminal. The feedback factor corresponding to an reduction is in amplitude of output signal, and negative can be reduced to amplitude of signal by adding a pair of resistance. Here we give two pairs of resistance R1 and R2. Then beta is equal to R1 by R1 plus R2. Op-amp parameters. CMRR, common mode rejection ratio, ratio of open loop gain M to closed loop gain ACM. CMRR equal to M by ACM. CMRR is usually expressed in decibels. CMRR decibel equal to 20 log 10 M by ACM decibels. For typical op-amp, value of CMRR is 90 decibels. Power supply rejection ratio PSRR. A basic op-amp circuit, a variation in the input voltage VEE have same effect as an input voltage change. Thus, variation in VCC and VEE to produce same changes at output. The PSRR is ability of an op-amp to reject variation in power supply voltage. That is, when there is a change in power supply, the PSRR rejects an variation. Ideally, the supply voltage should not change with the change in input voltage. PSRR equal to output voltage by voltage supplied. That is PSRR equal to V0 by Vs. If a variation of 1 volt in VCC or of VEE causes a output to change by 1 volt, then PSRR is 1 volt per volt. For MA741 op-amp, PSRR equal to 30 microvolt by volt per volt. Input offset voltage. The differential voltage that must be applied between the two input terminals of an op-amp to make the output voltage 0 is called input offset voltage and denoted by Vios. That is the differential voltage that must be applied to get the output as 0. Input offset current, the algebraic difference between the current flowing into the two input terminals of the op-amp is called input offset current and denoted by IIOS. That is the algebraic difference between the current flowing the two terminals. Output offset voltage. The presence of DC voltage at the output terminal with both the input terminal are grounded is called output offset voltage. Slew rate. Slew rate of an op-amp is the rate of change in the output voltage with respect to change in input voltage. It is measured as the voltage change in given time, typically volt per minute. Slew rate equal to change in output voltage by change in time at maximum voltage per minute. Drift compensation in op-amps. Being semiconductor device has the operating temperature of the op-amp changes with slight change in behavior of the op-amp is observed. If there is a change in temperature, there will be a slight change in behavior of the op-amp. Any changes in op-amp performance with temperature falls under the category of op-amp drift. Drift parameters can be specified for bias currents, offset voltage and like. Consult the manufacturer data sheet for specifics on any particular op-amp. To minimize the op-amp drift, an op-amp with minimum drift is observed and operating temperature changes are kept small. That is, to reduce the op-amp drift, we have to choose an op-amp with minimum drift by observing an operating temperature, keeping the observing and operating temperature small. The drift compensation techniques are developed for bipolar inputs that we have two polarity inputs. If there is a device mismatch is creates on input related to offset, the temperature drift is exactly proportional to the initial offset. So, at the output of the input stage, a resistor network is trimmed to give exact zero output or for zero input. That is, a network of resistor is kept to get the output as 0 when input is given as 0. This reduced both offset and offset drift. In this way, drift is compensated. Frequency compensation in op-amps. This technique, which the bandwidth of the op-amp is reduced proportionally to eliminate the ill effect of oscillations and to reduce the high frequency noise from being amplified. This technique is used in op-amps to avoid the high frequency noise effects. The multi-stage amplifier inside an op-amp can At high frequency, turn the useful negative feedback of the design circuit into an unwanted positive feedback due to the overall phase shift through the multi-stage. Frequency compensation can be internal to the chip by the manufacturer or external by the user or both. It consists of adding one low-pass RC stage in series to force down the bandwidth to a lower value, and hence higher frequency are not amplified or appear as noise. Usually, a low-value external capacitor is added to achieve the effect as the resistor value is built inside the chip. It is very useful in medical instrumentation where the signal produced from human body is of very low frequency and our highly bandwidth of the op-amp is only to invite troubles. Instrumentation amplifier. Instrumentation amplifier is a special kind of differential amplifier with additional input buffer stage optimized for high input impedance and high CMRR. The addition of input buffer stage makes it easy to match the amplifier with the preceding stage. Instrumentation is commonly used in industrial test and measurement application. This is the simple block diagram of instrumentation amplifier. It consists of input stage with the transducer and preamplifier, intermediate stage in instrumentation amplifier, output stage, undirected and automatic process controller. Here the physical quantity is given as input and the output is given at the output stage. This is a circuit diagram of a instrumentation amplifier. A1 and A2 form a buffer circuit, and bias current of instrumentation amplifier is determined by the op-amp A1 and A2. Here the resistance R1 starts shorted at R1 is removed. Here R1 is removed and RG is removed, and this result in fall in series negative feedback path, and the gain of the A1 and A2 will be unity. And when the circuit is shorted, the A1 and A2 gives a unit gain. The removal of R1 and RG simplifies the equation AV equal to R3 by R2. Important features of instrumentation amplifier is it has very low DC offset, low drift, low noise, very high open loop gain, very high CMRR, very high input impedance in million ohms range.